that the best way to explain an identity is really with this set of expressions at the bottom of the page and the differentiation between them. Specifically, when I highlight these two sentences, generally speaking, this one looks like an equation, this one looks like an equation. The difference between them is sine is equal to cosine once. There's only one answer where the sine value and the cosine value actually have identical answers. And that answer is at 45 degrees or pi over 4. That makes it an equation. An equation has an answer, singular. This second line has as the equation tan is equal to sine over cosine. Turns out if you were to graph sine divided by cosine and then graph as a secondary equation tangent, they intersect everywhere. They are the same graph. They don't have a single answer. They are the same everywhere. And that means that this is an identity. So the big difference between an equation, sine is equal to cosine, and an identity, tan is equal to sine over cosine, is how many answers are there. Back in September, we did a whole bunch of algebra problems where we got the answer to be either 7 equals 7, in which case I instructed you to say that this was true. Yup, it's going to work. And I said that meant no matter what you put in for x, it's going to work. Do you remember talking about that?
Yes.
And then we got a different set of answers where 0 is equal to 10, and we said, well, that's not true. And that meant it doesn't matter what you're going to put in for x, that's never going to work. The ones that were identities were the ones that were true. And when you say true, you're saying always true. What we're going to be studying today and what we're going to use algebraically is identities. I'm going to try and explain to you what we've covered that has been an identity. I'm going to give you a cumulative list of all the identities, and then here it comes again. We're going to use those identities to simplify algebraically our trig. So the trig's coming back one more time, and no, this won't be the end. Algebra, 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 it's always coming back to haunt you. This is going to come down to the following. We're going to define an identity to be an equation that is true with an S ooh, goodness gracious. For all values of x or theta, depending on what it is you're plugging in. When we're doing a unit circle, the Pythagorean identities, the new ones that we're going to add into our vocabulary today, come from the unit circle. Virtually everything in trig these days comes from the unit circle, and it comes from the fact that in a unit circle whose radius is 1, the horizontal distance to get to that point is x, but we've actually labeled it the cosine of theta, and the vertical distance to get to that point is y, but we've actually labeled it as the sine of theta. Does everybody know where I'm getting all that from? Hopefully I haven't said anything that is unique or new to you, because this is what we've been doing for about 2 weeks.
No.
So if I'm going to now apply the Pythagorean theorem to this particular triangle, instead of saying x squared plus y squared equals 1, I'm going to say that cos squared plus sine squared equals 1. Squared, but that's just a 1. That is our first, our fundamental, and our primary Pythagorean identity. There are 3. The other 2 come directly from this one. But the most important thing I need you to see is where that one came from. So everybody see it? Now in English, what that means to you, a little sidebar note here, the squared term comes after the trig function but before the angle. And notationally, the reason for that, let's pretend that theta was a 60, is because it's really easy to see that it's the squared on the cosine, meaning find the cosine of 60 and square the cosine, square the answer, square the value. Where if I put the 2 here, it looks like I'm going to square the 60, the angle, and I'm not squaring the angle, I'm squaring the answer I got when I took the cosine of 60. So notationally on paper, we're going to put the squared there. I do want you to know when you go to type this into your calculator, you have to type it as cos 60, close the parentheses, that means I'm done with the 60, and then square it.
Like, if we don't want to get mixed up, can we just write cos 60 in parentheses?
The whole thing in parentheses, that's fine too. But this is how you're going to see it when I do it, and I want you to know that. Okay, so the easiest thing for me to do to show you how this plays out and that it really does actually work is to ask you to flip back in your notes to this page where we had the circle with all the values on it. And if I haven't flipped back to this page already, it's important for you to see that essentially this is a unit circle where I have identified on this unit circle just about every important or special angle in degrees. I've then identified that same angle's radian value, and then I've told you the coordinates of the point that land on the unit circle. That means the cosine of 30 is rad 3 over 2. It means the sine of pi over 6 is 1/2. And Pythagorean identity goes here. If I were to take the cosine and square it, and then take the sine and square it, you'll never guess what I'm going to get. I'm going to get a 1. And that's true all the way around the circle. It works for every one of these point values. Pythagorean identity. You see it? Okay. So that's how the Pythagorean identity works. It's what it is. And what I'm going to do now is show you the other 2. The other 2 Pythagorean identities come specifically from, that plus sign is driving me crazy, from taking this 1 and just manipulating it a little bit. So the first thing I'm going to do is say I really don't like this cosine. So I'm going to divide straight through by the cosine squared function. And when I divide straight through by the cosine squared function, I'm going to get my second Pythagorean identity, which is cos squared over cos squared becomes a 1. Sine squared over cos squared becomes, what is sine over cos? Tan. So sine squared over cos squared is tan squared. And 1 over cos squared will be what's 1 over cos? I heard it. Secant, thank you, Joe. So 1 over cos squared will be secant squared. That's my second Pythagorean identity. 1 plus tan squared equals secant squared. It's really the same exact function. I've just divided straight through by cosine. Anybody want to speculate where I'm going to get that third function from? Let's divide straight through by sine. And when I divide straight through by sine, I get cos squared over sine squared is cotangent squared. Nice job, James. Sine squared over sine squared is a 1, and 1 over sine squared is a cosecant squared. And if you take a real good look at these 3 Pythagorean identities, what you'll see is that all 6 trig functions are represented in there. They're just squared. Everybody see it? I got your sine function, I got your cosine function, I got your secant function, I got your cosecant function, I got your tangent function, I got your cotangent function. They're all somewhere in those Pythagorean identities. Check. Okay, so how are we going to use them? Well, essentially, we're going to have two general rules of thumb. There's a couple of things we're going to do with these things. The first is use them to simplify trig expressions. And simplified trig expressions means exactly what it meant back in algebra. It means basically factor if you can, cancel if you can, reduce if you can, combine if you can, common denominator if you can, and make it into a non-fraction if you can. That's all simplified. So just talking quickly about the hierarchy of simplification. One term, common denominator, has been combined, is always better than two terms. Non-fractions is always better than fractions. So your best, simplest answer would be a single term that's not a fraction. Does that make sense? Your second best answer would be a single term that is a fraction. Your third best answer would be two terms, but they better not be fractions. And if you really can't do anything, you'll have two terms that are fractions. But you know what? I'll never see that. Because if you have two terms that are fractions, what should you be doing? Common denominator. That makes sense. Okay, now, things to watch for. Generally speaking, our first rule of thumb is we're going to do this by changing everything to sine and cosine, because everything can be written as sine and cosine. What if I get a cosecant? It's 1 over sine. What if I get a cotan? It's cos over sine. What if I get a secant? It's 1 over cos. Everything can be put in terms of sine and cosine. Bringing it down to just two functions allows me to cancel, so I'm going to do that. The only exception to that is going to be if I see squared terms. And if I see squared terms, I might want to use these instead. I might want to replace with the Pythagorean identities. So nothing is squared, go sine and cosine. You see squared terms? Think about these. Those are our two general rules of thumb. Here's how it plays out. If I give you a question like, turning the page, I've done one for you. Simplify cosine times tan. Now, keep in mind here, my goal is to simplify. That is already one term that's not a fraction. Some of you might say, I already got what she said is going to be best. I'll stop. Nope. If it says simplify, you're going to do something. But what can I do? Well, I can leave cos, and I can make tan into sine over cos. Because when I do that, guess what happens? Cancel. And now it's a slightly smaller single non-fraction term. Do you see it going on there? Okay. Now we're going to try doing one ourselves. I want you to know when you read this that the directions in terms of sine, cosine, or both is the directions on the how-to. I do not want all of your answers to be in sine or cosine. I want your answers to be as small as possible. Preferably a single term that's not a fraction. So after you have canceled, I want you to put it back into whatever trig function you can that'll shrink it. But they are going to tell you to use sine and cosine to do that. That's how you read those directions. So what they're telling you here is change cosecant to 1 over sine. Does everybody see where I'm getting that from? Change tangent to sine over cos. And then, if possible, cancel. Can I? I can. I'm now down to a single trig function in a single term that is a fraction. I think I can do better. I can make it not be a fraction by calling it a secant. And that will be my answer. So again, what it says here is change everything to sine and cosine. That's the work. It's not necessarily your answer. You're allowed to have secant, cosecant, cotangent, and tangent be part of your answer. Is everybody okay with that? That's what I'm asking you for. Let's try the next one. This one is a sum question, and they're starting you with tan plus cotan. So I'm going to start by writing that in terms of sine and cosine. So I'm going to change tangent to sine over cosine. I'm going to change cotangent to cosine